Alright, so in video 5.4 we talked a lot about this sort of big picture of a really small picture, the quantum mechanical model of the atom, which really sort of brought together a lot of these threads that electrons are particles. They're really tiny, but they behave more like waves than they do like particles. Those waves can interfere with each other, and that gives rise to these complex three-dimensional standing wave structures inside of the atom where electrons can only exist in certain places. And we said that those wave functions, really the sort of mathematical definition of that wave, which is derived from the Schrödinger equation, those are defined by a set of whole number values that we call the quantum numbers. And quantum numbers, there's actually 4 of them, but we've only talked about 3 so far, and we said the sort of practical use is they're like the zip code of an electron or an orbital. And we said that that wave function itself, if you square that mathematical function, that really is the probability of finding an electron in 3D space. That probability of finding an electron in 3D space is what an orbital is. So the shapes of orbitals, which we're going to talk about in a second, are really just probabilities. They're not actual containers that hold an electron in space. Instead, they're really just the result of a complex interference pattern of those waves in space that give rise to that wave only existing in those places. And we also then said that the specific quantum number that we need to think about in terms of 3D space, or where these things reside, or really the shape, is this angular quantum number, or angular momentum quantum number, L. And we also said that L can take on any value up through n-1, which gives it the ability to take on several different integer values depending on what the principal quantum number n is. But it could take on 0, 1, 2, 3. Each of these L values corresponds to a distinctly different shape. We give these different notations, which are really what we are accustomed to calling different orbitals. So we have the s, the p, the d, the f, we have g and h orbitals as well. But we'll mostly deal with these 4 in this class, and really probably mostly s and p and a little bit of d. These shapes correspond, I alluded to just briefly, we're going to elaborate on those. An s orbital is a purely spherical shape. A p orbital has this sort of dumbbell shape. And then D and F orbitals have dumbbell shapes, but they're complex, and they have more than just 2 lobes. They either have 4 lobes or 6 lobes or more, and their shapes can change slightly. So let's talk about these individual orbitals and what they look like. So s orbitals, as I mentioned before, s are these spherical shaped orbitals. The depiction that I grabbed from a book here, shows them as sort of fuzzy surfaces, and that's to give you a better sense that these aren't these rigid containers that sort of hold electrons in, bouncing around. Instead, they are probability functions where electrons could potentially reside with a non-zero probability. And so when we have a 1s orbital, that means we have an n equals 1, L equals 0. 1s means we have sort of the simplest sphere where the nucleus is in the center and the electron can exist anywhere inside of that sphere. So the bottom is sort of a cross-section view, and the top is the full view of what that electron probability might look like. If you were to be able to even zoom in, which we can't, we don't have tools for this scientifically, you wouldn't actually see anything at all, because really what you're talking about is a single particle in the wave interference of this pattern. So it's really easy to fall into this trap to think that this is actually the shape of the orbital. It's not really, it's just a function. It's a representation of a function, just like you would have a representation of a 2-dimensional function, like a parabolic function or a hyperbolic function, etc. So it's just a 3-dimensional function. So if we have an n equals 2, remember I talked about n, the principal quantum number. It's sort of like this onion skin. It's representing the size and the energy of those particular orbitals. And so n equals 2, we have the original one s orbital buried here in the center, and then we have the 2s orbital as this blue diffuse layer on the outside. And you can see in the cross section then that we have this white area, and the white area we call a node. So a node is the place of 0 electron probability. It's that part in the onion right between the two layers of skin, and what we're saying is that that's when the probability function goes to 0. And so an electron cannot exist there. It's actually quantum mechanically forbidden to exist inside of that white area. Those are nodes. Nodes are really important because you'll see that the more nodes an orbital has, the higher energy it has to exist. So this n equals 3 option here, you can see that 3s orbital has 2 nodes of 0 electron probability inside of it. And so this is what the actual 3s orbital would look like as a probability function. Another way to think about nodes, remember these are 3-dimensional wave interference patterns, but if we thought about this just in simple 2 dimensions, we could think about our normal standing sine wave. And every time that wave sort of crosses over and goes through 0, that's considered a node. And so you can think about each of these white spaces in these higher order orbital shapes. That's when there's 0 probability of finding any amplitude of that particular wave. Okay, so when the angular momentum quantum number is equal to 1, so L equals 1, then we give rise to this P shape, or these P orbitals, and we already said that these are dumbbell in shape, meaning they have 2 distinct lobes. And so I'm showing you, remember, if you have an angular quantum number of 1, then that means your magnetic quantum number can take on any value from plus L to minus L, which means we would have everything from -1 to 0 to +1, which means that the original dumbbell shape that a p orbital has, like this, could actually exist in 3 different orientations. And that's what we're seeing here. We're seeing these 3 distinct orientations of our p orbital shape. So we could say that this is arbitrarily assigned. There's actually no correlation here, but we would just say that maybe this one is the -1, this one is the 0, and this one here is the +1. And all that means is that you can see that the 2 lobes in this first instance, in the m sub L equals -1, these are pointed along the x-axis. That's one distinct spatial orientation. Remember that the m sub L, the magnetic quantum number, is spatial orientation. It has nothing to do with the shape, just how that shape is arranged in 3-dimensional space. So if here it's oriented along this x direction, we'll say that's m sub L -1. Another shorthand for that is to write this as a p orbital with a subscript of x. We call this the px version of that orbital. Similarly, we could look over here and we could identify the bulk of the electron probability is now lying along the y-axis. So we could call this the p sub y, and the same goes for the p sub z. So we have 3 different orientations of any p orbital. They could lie along any one of the 3 Cartesian axes, and that's where we get these 3 individual magnetic quantum numbers. We can't have any more magnetic quantum numbers than 3 for L equals 1, meaning we are constrained to these 3 different orientations. And this is going to be the case whether or not we have a 2p set of orbitals, a 3p set, or a 4p set. The p, again, just denotes the shape. It just says it's a dumbbell. The number in front of it just tells us the size and the energy, but it's the magnetic quantum number that's attached to it that will tell us the specific orientation. So if you had an atom, we'll say that's the nucleus here, this blue dot. If you had an atom that had electrons in the 3p orbital, that would mean that also it must have electrons in the 2p orbital, because the 2p comes first, and we're going to fill from the bottom. And so that means we would have, that would also mean that there's going to be electrons in the 1s and the 2s, and we'll talk about this later. So that means we'd have electrons, we'll do this in green, we'd have electrons in that 1s orbital here, we'd have electrons in that 2s orbital, which is that bigger shell here. So there's 1s, there's 2s. That means we'd also have electrons in the 2p orbital. The 2p, we'll say that's the x, the 2p y, and the 2p z. And then we'd also, on top of all of that, have electrons in the 3p, which means we'd have them in the bigger orientation as well. And so it's important to remember that electrons aren't just in the outer or highest energy orbital, they're filling up everything below it as well. And so you get a superposition of all of these different orbital shapes on top of each other. Anywhere between the orbitals, we have again these nodes. And so we saw on the s orbitals, specifically the higher order s orbitals, in cross section, we had these white spaces in between. We called those nodes. In between every p orbital, we have these things called nodal planes. So you can see actually p orbitals have two different lobes, and the two different lobes are colored differently because we call these different phases. And we're not going to talk a lot about the origin of why they have phases. We often call this a positive phase and a negative phase, even though they're not charged. We just use that to assign them to being different. It is important, though, that when we get to bonding later, a bond in a molecule literally is when an electron in one phase of an orbital overlaps with an electron in another phase, exact same phase of that orbital. And so bonds are formed when like phases overlap in orbitals between different atoms. And so phases become really important when we talk about bonding in chapters, let's see, probably 7 and 8. Okay, so the third most common type of orbital that we're going to talk about in this class are these d orbitals. So that's when the angular quantum number is equal to 2. And remember, then the m sub l can take on values of -l up through +l, which means we could have 2, 1, 0, -1, and -2, which means that, again, don't forget, this magnetic quantum number talks about orientation in 3D space, and L tells us about the shape. So the shape is the d orbital shape, and the orientation tells us how this thing is arranged in space. If we have 5 of these different orientations, sorry, this one is an f orbital, then we have these 5 different shapes here, A through E. So these are the 5 different orientations of d orbital. You can see as we get higher in order and shape, then we get more nodal planes, more nodes, which means higher in energy, but it also means there's less space for those electrons to exist in, and this is the general trend here. You can see that this is called the dxy orbital. The reason is because these 4 lobes, these dumbbell lobes, are lying in the x and y plane. Just in the same way, the dyz orbital has the same shape, but now these are lying within the y and z planes, perpendicular to the x plane, or the x direction, I should say. We have the dxz, which is lying in the xz plane. And then we have this sort of weird one where we have the d x squared minus y squared. It's the same shape, but instead of lying in the plane perpendicular or 45 degrees rotated to the axes, they're actually lying on the axis themselves. So if you look at the x squared minus y squared versus the xy, they're exactly the same between these two, except this one is rotated 45 degrees within that xy plane. And then the last one is the oddball. This is sort of an interesting one, and it has big implications, but it's actually a different shape, and this comes just from the math of deriving this probability function. This is the dz squared orbital, and it looks a lot like a traditional p orbital with the dumbbells, but then it's got this torus around the center, which is a different phase. And that's what that is right there. Some really interesting bonding that occurs in the dz squared. Okay, so the general takeaway here is, you've got this new shape, L equals 2. These are d. The magnetic quantum number can take on 5 different orientations. That gives rise to literally the 5 different d orbitals. So the fact that we have 3 p orbitals comes from the fact that we have 3 magnetic quantum numbers. The fact that we have 5 d orbitals comes from the fact that we have 5 different spatial orientations or magnetic quantum numbers for an L equals 2. So you could sort of predict then where we're going. If you have an L equals 3, which is the F, how many specific F shapes should we have, or orientations should we have? So think about that. I'll pause it and then I'll bring it up in a second. Okay, so I'm showing you all of the different orientations of those 4 different shapes of orbitals here, or subshells. So if we have L over here, I'll just write L, that's our angular momentum quantum number. We have L of 0, which is the s orbital. We have L of 1, which are the p orbitals. We have L of 2, which are the d orbitals. And we have L of 3, which are the f orbitals. And then remember, m sub L, that can take on anything from minus L up through plus L. So this can only be 0. So that gives rise to only one orientation, and that makes sense because it's a sphere. You can rotate a sphere in any orientation, it's still the same sphere. If we look at the p orbital here, that can be -1, 0, and +1. There's 3 different orientations of that dumbbell, which is why we have 3 different p orbitals. The d orbital, L equals 2, that's we'll just say ±2, ±1, and 0. That's 5 different orientations, which gives rise to the 5 different orientations of our d orbital. And then F, which is the sort of question I left you at, has ±3, ±2, ±1, and 0, a total of 7 different orbital orientations. You can imagine if we went to L equals 4 and G, then we would have ±4 all the way through 0, which would give us a total of 9 different orientations of the g orbital. Okay. So remember, I mentioned that the orbital here, all of these shapes are probability functions to just tell us where an electron can exist. And it's important to note now that in each one of these distinct orbitals, each one can house exactly 2 electrons. It can either hold 0, 1, or 2, but no more than 2 electrons. And so I told you before that no electron inside of an orbital can have the same set of quantum numbers. So if I put 2 electrons into this s orbital here, at this point they would have the same set of 3 quantum numbers. That means we need 1 additional quantum number to differentiate these 2 electrons from each other. So that's where we're going next. So quick recap, we've got the 3 principal quantum, or 3 quantum numbers that we've talked about up to this point, and we talked about them as sort of this unique zip code where the principal quantum number n tells us about the energy and size, but nothing about the shape or orientation. In that case, we need the angular momentum quantum number L that tells us the shape, whether it's a sphere, a dumbbell, or a double dumbbell. And then, even then, we need to differentiate the orientation for those things that aren't symmetric, how they're oriented within the x, y, and z space. But then we just talked about how, well, 2 electrons can fit within each one of these orbitals, but we can't have the same set of quantum numbers for any particular electron. In that case, what happened was scientists in the early days, and thinking about the quantum mechanical model of the atom, they looked at what they call the fine structure of the line spectrum. Really what that means is they just zoomed in really close, and what they saw was that at every line, on say like the hydrogen, we don't need to think about deuterium for now. On the hydrogen lines, they actually saw two very closely spaced lines. And that gave rise to the prediction that there's actually a fourth quantum number, and they call this the spin quantum number. And the spin quantum number goes with the shorthand of m sub s. So we have m sub l and m sub s. Spin in quantum mechanics is not the way that we think about spin classically, but we're going to use a classical model because that's what most people do, because it really doesn't have a very easy meaning to think about without doing some math. So in the classical state, we could think about an electron being able to exist. So if you've got an electron, remember, two electrons can fit into each one of the orbitals that we just talked about. And for each electron, we can say that it can sort of spin in two different ways. It can either spin in an orientation sort of like a magnet, where its polarity is facing upward, or it could spin in a direction where the polarity of its field is facing downward. And that's what these two pictures are representing here, in which case the electron can't exist in any other state in between. It can't go sideways or the other way. It can only exist to spin up or spin down. And so we call these two states plus half and minus a half. And the specific numbers aren't pertinent here unless you go on to take a more advanced course. We're just going to call this spin up and spin down. And that's important because now those two electrons that can exist in all of those subshells that we just talked about, those can either exist in up or down, which means that in an orbital, we're going to have both one electron facing up, that we usually denote with a half arrow pointing up, and one electron pointing down. What that allows us to have is each of these electrons, even though they share the first three quantum numbers identically because they're in the same subshell with each other, that last fourth quantum number here is different. And that means that those two electrons don't have the same set of four quantum numbers. We call this principle the fact that two electrons can't have the same set of four quantum numbers. We call it the Pauli exclusion principle. So Pauli exclusion principle is exactly what we just talked about. So electrons have four unique quantum numbers or zip codes. That's important. And that has important implications for when we get to how do electrons fill the subshells in an atom. So how do we actually put them into their structure? Now that we're sort of thinking about the general structure for how electrons can arrange themselves, now when we think about a multi-electron atom, we're going to actually need to add them to the atom and think about exactly how that occurs. And the Pauli exclusion principle is going to be really important for that.